Hello friends, this is the basic problem and operational of amplifiers. This can be solved easily by simply applying the properties of operational amplifier. So the very fundamental property of operational amplifier is it won't take any current to conduct. So the input terminals draw zero current, and so whatever the current flows through this direction is nothing but, let's say this is I2 is nothing but V2 over R plus R, so V2 over 2R. So clearly at this point the voltage is V2 over 2. This is a simple voltage division rule. Now another fundamental property of operational amplifier is V plus is nothing but V minus. So now here the voltage is V2 over 2. So simply to calculate the relation between V1 and V2 at output side, we simply write a KCL equation here, Kirchhoff's current equations, so nodal. So V2 over 2 minus V1 upon R plus V2 over 2 minus V0 R is equals to 0. So by minimizing the terms, I'll get V2 minus V1 minus V0 is 0. By rearranging the terms, we can easily write the relation between V1 and V2 with V0 is V0 is equals to V2 minus V1. This is most important equation for this problem. So now the very first part of the question is now solved, that is express V0 as a function of V1 and V2. So now the second part of the question is, what is the input resistance seen by V1 alone? So another important thing of operational amplifier is basically it is a linear device. So now we will make this V2 equals to 0. Only V1 active alone now. So in this case, some current must be flowing this direction, as we are aware that operational amplifier will not take any current for its operation. So the input current I1, let's say this is I1, which is supplied by the voltage source V1. So V1 over R, because now this voltage is 0 volt, so this must be a 0. So this current must be I1 is nothing but V1 over R. RI1, the input impedance, input resistance seen by V1 alone is V1 upon I1 is nothing but R. So this is the answer for the second part of the question. Now let's check what is the input resistance seen by V2 alone. In this case, see, in this case let's nullify V1 is equals to 0, so it will be grounded here. So in this case, as usual, this voltage must be V2 over 2 as we calculated earlier. So this current is now I2. So clearly I2 is nothing but V2 minus V2 over 2 upon R. So clearly I2 is nothing but V2 over 2R. So V2 over I2, which is nothing but input impedance seen by the voltage source 2, that is 2 times R. So this is the answer for the third part. Now the most important and interesting part, that is the final part. So in this case, simply we are connecting a voltage source across the terminals. So now this is V. So to calculate the input impedance seen by this source, the input impedance is nothing but R in is V upon I. So in this case, it is one more time I want to explain that this current and this current are zero. Whatever the current is flowing like this. So in the shown path, let's write a loop equation, that is I. This current is I, basically flowing across the loop. So that is I times R, this R covered, and now this R, and this voltage source is minus V. Basically this is V, so we are writing from negative to positive terminal. Again I is flowing through this resistance and this resistance, plus V0 is equals to 0. So in this case, it is clear that 4IR minus V plus V0 is equals to 0. But earlier we have calculated that V0 is nothing but V2 minus V1. So this is your V2, this is your V1. So V0 is nothing but V2 minus V1, so which is nothing but minus V, because V1 minus V2 is V here. So the equivalent equation now becomes to 4 times IR minus 2V is equals to 0. So V over I is nothing but 2 times R. This particular resistance we call as RID is equals to R, which is differential mode input impedance. That's it. Thank you for watching. Please subscribe my channel.